Welcome to this explainer. Okay, if you're an AI and ML student right now, I know that clock is ticking hard on your human-computer interaction exam. Paper code PCCS AML 302A, right? You're probably staring down a syllabus that feels, well, like an absolute mountain, and a massive index of past papers. But hey, take a breath, don't panic. Today, we're going to be your strategic cheat code. We're going to decode the whole HCI syllabus together, dig into the matrix, and intuitively grasp these underlying principles so you can absolutely crush those 10-mark questions.
Let's kick things off with a weird question. Have you ever noticed that the old Windows 95 Start button was mathematically impossible to miss? I mean, most people just assume Microsoft jammed that iconic button into the bottom left corner for, pure aesthetics. But no, it's actually a deliberate, brilliant biological hack. Once you start looking at software through the lens of human psychology, the interface stops being just a random collection of pixels and starts looking like a highly deliberate psychological maze.
It's all about this concept called the infinite edge hack. Before we look at a single line of code, we have to look at how designers literally exploit human motor movement. See, because that button is jammed exactly into the corner of the monitor, the physical edge of the screen acts as an invisible, infinite wall. Your mouse literally cannot go any further left or down. So mathematically speaking, you can just violently flick your wrist toward the bottom left, and the operating system will stop your cursor perfectly on that button. It literally drops the required cognitive effort and movement time down to almost zero.
To get you exam ready, we've organized our agenda around 5 high-probability topics from your past papers. 1. The human engine. 2. The math of movement and choice. 3. Cognitive architecture. 4. Web and mobile paradigms. And 5. Usability and networks.
Let's jump right into Section 1, the human engine, biological hardware limits.
Look, before we prototype anything or write a single line of React, we have to understand the literal biological limits of the user's eye. There's this tiny pit in our retina called the fovea, and it gives us our absolute sharpest, most detailed vision. But here's the catch. It covers only a tiny 1 to 2 degrees of our visual field. Everything outside that, that's peripheral vision. It's great for detecting motion, sure, but it is terrible for fine details. And since Western languages read top to bottom, left to right, our default foveal focus is glued to the top left. So as a designer, you are literally fighting to guide the user's eye. If you bury some critical error message way down in the bottom right, you absolutely have to use bright colors or animations to catch that peripheral vision. Otherwise, the user is functionally blind to it.
Moving right along to Section 2, Math of Movement and Choice, Fitts, Hicks, and Miller's Laws.
Okay, listen closely on this one because examiners absolutely love it when you drop mathematical formulas into your answers. Hicks' law tells us that more interface choices exponentially increase decision time, right? But the crucial one for physical navigation is Fitts' law. It perfectly models human motor control by predicting movement time to a target. The formula is mt equals a plus b times log base 2 of d over w plus 1. Let's break that math down. D is the distance to the target, and w is the target's width. Because of how that logarithmic fraction works, if you make a button bigger, meaning you increase W, the fraction gets smaller and boom, your total movement time decreases. So bigger buttons, placed physically closer to the user, equal way faster interaction. That is the exact mathematical proof behind the infinite edge hack we talked about earlier.
Now, shifting from physical movement over to memory, we hit George Miller's magic number, which is 7 plus or minus 2. This is Miller's law. Back in 1956, Miller proved that human short-term working memory can really only hold about 5 to 9 chunks of information at once. Try to cram in any more than that, and the brain literally starts dropping packets. This is exactly why we format a 10-digit phone number with spaces. We intentionally chunk it into 3 distinct groups to bypass our biological hardware limits and stop our short-term working memory from crashing.
But humans aren't just reacting, right? We're actively reasoning. For the exam, you've got to know the difference between these 2 types of reasoning. Deductive reasoning is top-down. That's when you apply a known rule, like, hey, blue underlined text means it's a hyperlink, to a totally new website. Inductive reasoning, on the other hand, is bottom-up. It's learning through trial and error, like randomly clicking a weird gear icon just to figure out it opens a settings menu. Truly catastrophic interfaces are the ones that actively punish inductive reasoning. Think about it. If a developer makes a trash can icon copy a file instead of deleting it, they just shattered the user's deductive rules and completely ruined their inductive trust. Not good.
Next up is Section 3, Cognitive Architecture, Modeling the User's Mind.
You might want to draw 5 stars next to this in your notes, guys, because it is an incredibly high-probability exam question. We're talking about how we scientifically model a user's thought process. First up is the clash between the mental model and the system image. The mental model lives entirely inside the user's head. It's how they believe a system works.
The system image is the external reality, the actual UI on the screen. The entire goal of HCI is to make that system image perfectly align with the mental model. A great example, the desktop recycle bin. It's basically a benevolent lie. Our mental model tells us we're physically dragging a file into a trash can. The system image plays along with a cute little paper-filled icon. But technically under the hood, the OS just updated a directory pointer. The interface is literally abstracting the complex code just to protect our cognitive load.
So how do we actually measure the efficiency of a design? We use the GOMS framework. That stands for Goals, Operators, Methods, and Selection Rules. It basically lets you compile human actions the same way you'd compile a computer program. If your goal is to delete a word, your operators are the atomic physical actions to get there, like moving a mouse or hitting a key. Your method is the sequence of those operators, and selection rules tell us which method an expert is going to pick. And because researchers have assigned exact milliseconds to every single operator, like exactly 1.1 seconds to point a mouse, you can use GOMS to mathematically prove, beyond a shadow of a doubt, that using a keyboard shortcut is vastly faster than clicking through a drop-down menu.
We can even translate human cognition directly into a computer architecture stack. For you AI and ML students, John Anderson's ACTR theory is going to make instant sense. In ACTR, your attention is basically a single-thread CPU bottleneck, your working memory, that's your incredibly fast but highly limited RAM, and your declarative and procedural memory acts as your mass storage hard drive. If you write a program that dumps too much data into a user's RAM all at once, their CPU just completely chokes. And in human terms, that system crash, yeah, that's what we call cognitive overload.
All right, moving on to Section 4, Web and Mobile Paradigms, Building Real-World Interfaces.
Stepping away from internal brain mechanics for a second, let's look at how the actual conversation between humans and machines has evolved. Back in the 1970s, the command line interface required cognitively exhausting recall memory. Then the 1980s totally revolutionized things with WIMP, windows, icons, menus, and pointers. That shifted the heavy lifting over to visual recognition. By the 2000s, touch devices made our actual fingers the pointers. And now, welcome to the 2020s and ubiquitous computing. This is the era of the smart home, where computers vanish into the environment and interfaces become completely invisible and context-aware.
But honestly, regardless of the era, interfaces usually fail in two very specific spaces, known as Norman's gulfs. First is the gulf of execution, which happens right before an action. The user is just staring at the screen thinking, what can I do here? We bridge that gap by using obvious affordances, literally just making buttons look like they can be clicked. Then you have the gulf of evaluation, which happens after the action. Imagine you click pay on an expensive flight booking, and the screen just freezes. You're sitting there agonizing, oh no, did my action actually work? The absolute only way to bridge that evaluation gap is with immediate, crystal clear system feedback.
To keep users out of those gulfs, we rely on the iterative design process. It's a continuous loop. Understand requirements, design alternatives, prototype, and evaluate. We use scenario-based design, which literally means writing narrative stories about our users to build empathy and catch flaws early. And we prototype like crazy to follow that classic Silicon Valley mantra, fail fast, fail cheap. Why? Because of the terrifying cost of change curve. Catching a flaw on a literal paper prototype costs you basically nothing. But trying to fix that exact same flaw after the code is fully deployed, that's going to cost you thousands of times more.
Let's look at structural web patterns, because I guarantee this will be on the exam. Take drag and drop. It feels super intuitive, right? But it's actually physically hostile for accessibility, because it requires sustained fine motor control. You always have to provide a direct selection, click-based alternative. Then you have display patterns. Overlays are kind of like aggressive club bouncers. They hijack the z-axis of your screen and totally block background interaction. Inlays, on the other hand, are polite. They expand content gracefully within the page flow, sort of like an accordion menu. And then there are virtual pages, which create the illusion of a brand new URL without actually reloading the HTML. And yep, that is the exact magic running your React single-page apps.
On mobile, notice how biology strictly dictates the code. We deliberately design around the thumb zone so people don't constantly drop their phones trying to reach the top corners. We use 48 by 48 DP touch targets for a very specific reason. It maps exactly to the 10mm width of the average human fingertip. We enforce a 4.5:1 contrast ratio so you can actually read your screen in bright outdoor sunlight. And all of this is enforced through a really strict hierarchy. A broad philosophical principle becomes a recognized standard, which narrows down into a platform guideline and finally solidifies into a strict, unbendable company rule.
All right, home stretch. We've reached our final section, Section 5, Usability and Networks, QA and Computer-Supported Cooperative Work.
So how do we actually scientifically prove that our interfaces work? Well, it all comes down to a pretty mind-blowing number, 85%. Bringing people into a usability lab is super expensive. So, do you need to test hundreds of people? Absolutely not. Nielsen's binomial probability formula proves that testing with just 5 average users will uncover roughly 85% of all severe usability flaws. The math totally checks out, because a single user has about a 31% chance of finding any specific bug. Once you test past 5 users, you just hit massive diminishing returns. Seriously, drop this math in your exam paper, the examiners will love it.
But hey, what about users who aren't average? That brings us to universal design and the incredible curb cut effect. Think about the physical world. Cutting ramps into sidewalks was done for wheelchair users, but it accidentally made life way easier for parents pushing strollers and travelers dragging wheeled luggage. Designing for the extremes of human ability accidentally creates vastly superior products for absolutely everyone. In the software world, Apple built voice-over text-to-speech specifically to help blind users navigate their phones. But that exact same core technology is what directly enabled Siri to read your text messages out loud to you while you're driving.
Now, when we model human collaboration, we use the Computer-Supported Cooperative Work, or CSCW, time-space matrix. You basically evaluate if the collaboration is happening at the same or different time and in the same or different place. For instance, a same time, different place app like Google Docs absolutely needs real-time, live cursors. A different time, different place app like GitHub needs a super robust version history. The context completely dictates the code. And don't forget Shannon's entropy here. Text channels lack the massive nonverbal bandwidth you get in face-to-face chats. That is mathematically exactly why human beings invented emojis. They function as essential emotional bandwidth compressors.
Okay, guys, you now have the ultimate blueprint to tackle this HCI exam. But before we wrap up this explainer, I want to leave you with one final, pretty provocative thought. We've spent this whole time discussing how to engineer interfaces that adapt perfectly to human biology. We use Fitts law to make buttons effortless, and we build huge safety nets for error recovery so we never really face consequences for our mistakes. We are constantly bending the machines to cater to our limits. But as we spend 10, 12 hours a day inside these completely frictionless digital ecosystems, are we becoming impatient with a real physical world that doesn't have an undo button? As we reshape the machine to fit us perfectly, are we subconsciously reshaping our own psychology to fit the machine? It's definitely something deep to mull over while you study. Good luck on your paper, trust your associative memory, and I'll catch you on the next explainer.